Hello and welcome once again to this course on networks and systems. This lecture is about the prerequisites for the course. We mentioned in the introductory video, and you might be aware yourself, that you need some basic calculus for doing well in this course, and you also need to know AC and DC circuit analysis. So, in this brief lecture, what I am going to try is to give you a glimpse of what the prerequisites are, mention a few of the important details, and after that you will have to be after that you will be able to go out and maybe look at some textbooks that we point you to, or look at some material on the internet that we point you to, and learn the prerequisites on your own. So, once again, this lecture is not a substitute for the prerequisites, it is only a pointer or a refresher of the basics that you will need for doing this course. So, let us see how it goes. Okay. So, like I mentioned, the prerequisites for this course are basic calculus, in particular you will need to know about functions of one variable. Now, you might wonder why in an electrical networks and systems course functions of one variable are very important. The answer is quite simple. The reason is, in any electrical circuit or network, the variables are voltages and currents, and these vary over time. Okay. So, in our course, this variable in most cases will be time. Later on, we might also have variables such as frequency, etc. But to start off, you can think of the variable that we have as time, and these functions in our case will typically represent voltages or currents in a circuit. Okay. So, you might have studied about circuits in your previous courses. Circuits are made up of circuit elements, and these circuit elements are basically voltage sources, current sources, resistors, capacitors, inductors, and these components, when connected together, result in voltages and currents in different parts of the circuit, and these vary over time depending on the situation. So, let me give you a few examples from the circuit world and point you to corresponding functions that you might see. Okay. So, once again, the style of this lecture is to give you a refresher of the basic ideas. So, I will not be very formal, I will not introduce or define things very formally, but simply point you to different aspects which possibly give you a glimpse of the prerequisites needed. Okay. So, let us take one of the simplest of circuit components out there, which is a voltage source. Okay. So, this is typically denoted like this, maybe you put plus minus and then you have a V. Okay. So, I am going to say this is a DC voltage source. Okay. So, this is a typical notation, and this V in volts is the value of the voltage across these two terminals. So, what does this mean? This means that if you measure the potential difference between these 2 points, you are going to get V volts as the answer, and that is going to be a constant for all time. That is the definition of this voltage source. So, let us say if I call the voltage between these 2 points as a function V of t. Okay. So, notice once again this notation I have used, the voltage across the voltage source I am calling as a function V of t, and this t is my variable which is going to be time, and this V is the function which denotes the voltage across these 2 points. In this particular case, this is a very simple function. We know what the answer is going to be. This V of t is going to be equal to V for all t. Okay. So, for all time t, this V of t is going to be equal to V, and that is the definition of the voltage source. So, now you might want to plot this function, and plotting functions is very important. It gives you a clear idea of how things work. So, to plot functions of one variable, you need axis you need the independent axis, the t axis, and the y axis which plots values of this function. Okay. So, now this v of t is going to be equal to v for all time t. So, you get what is known as a constant function whose value is v for all t. Okay. So, how do I read this function? This function v of t is equal to v for all t, and I have drawn a flat line at v parallel to the x axis. So, what does that mean? Suppose I go to t equals 10 and ask you what the corresponding value of v of t is, and that will tell you that this height, which is v of 10, is in fact equal to v. On the other hand, let us say I go to minus 20, which would roughly be here in time, and then ask what is the value of the voltage. That answer is again this height, which is again going to be v. Okay. So, that is this constant function. Okay. So, constant functions are the simplest functions, and like you saw here, across a DC voltage source, the voltage is a constant function. So, this is an example of a constant function. Okay. So, now there are other constant functions that would show up in a circuit, and you can imagine if I connect this voltage source to, let us say, a resistor. Okay, let me show you that. It is quite simple to see that. If I connect this voltage source, a DC voltage source of value V, to a resistor in this circuit like this, and maybe this resistor has resistance R ohms, then in that case, let us look at the current that is going to flow through the resistance. Okay. That is going to be denoted as a function I of t. Okay. Once again, I of t is the current through the resistance, and that function, you know from your basic circuit theory, is going to be V divided by R. Okay. So, once again, this is equal to V divided by R for all t, for all time t, which is again a constant function. And you can see quite readily that this is the constant function V of t multiplied by 1 over R. Okay. So, you see the constant functions in different parts of the circuit are related to each other in a simple resistive circuit in this fashion. Okay. So, once again, constant functions are the simplest functions out there, and one can see they show up obviously in a very easy way in simple DC circuits. Of course, if you complicate your resistive circuit here, you put a lot of resistances in series, parallel, etc., you might have to do a lot of solving to figure out what the currents in the different resistors are going to be, but nevertheless the currents are always going to be constants over time, the voltages are going to be always constants over time. Okay. So, that is a very simple example of a constant function. Okay. So, let me change things around a little bit, make it a little bit more interesting. Let us say we consider a voltage source like before, okay, exactly like before, except that I am going to add a little switch here, okay, and I am going to say I will throw the switch, or basically turn the switch on at t equals 0. So, let us say we turn the switch on at t equals 0. Okay. Now, I am going to ask the same question once again. Okay. V of t is the voltage across these 2 points, okay. And so now in this case things are a little bit different from before. In previous case we had a voltage source, and I said V of t is the voltage across the 2 ends of the voltage source for all time. So, now I have a switch thrown in, and that switch is off for t less than 0 for negative time, and from t equal to 0 onwards it becomes on. Okay. So, in this case one can justify this quite easily. How is V of t going to be? My function V of t, okay, when the switch is turned off, there is maybe no potential difference between these 2 points, okay, and that will tell me that V of t is 0 for t less than 0. Okay. So, once again there is lots of notation going on here. I am saying the function V of t equals 0 for t less than 0, and then what happens for t greater than or equal to 0? I might want to say that the value of V of t equals V. Okay. Once I throw the switch or once I turn the switch on, the potential difference between these 2 points is going to be equal to V volts. Okay. So, this is the function now, and you see this is not a constant function anymore, but it is quite close to a constant function. It takes two different values, one value for t less than 0 and one other value for t greater than or equal to 0. And if you were to sketch this or plot this or graph this function, it would look like this. Okay, you have the t axis here, you have the v of t here. For t less than 0, it is going to be equal to 0, and this line will be right on the x axis, and it might be difficult for you to see, and then for t greater than 0, it is going to be equal to v. Okay. That's your v of t, and this function you can see is clearly different from the constant function, and things start becoming very interesting very quickly with functions like this. Okay. So, you quickly see utilities of you quickly see the utility of thinking of voltages across points in a circuit as functions of time. This lets you deal with the practical notion of turning the switch on in a circuit. Okay. When you turn the switch on, what happens in the circuit? When you turn it on, how do the voltages across different components in the circuit change over time? That is a very relevant question when you design or build an electrical circuit or network, and you should know the answer to that question. So, in this course you will learn things like that. When the voltage across 2 points in a circuit varies in this fashion as opposed to being a constant, if it varies from 0 suddenly to V, what happens in your circuit? Your circuit is going to react in a dynamic fashion. It will do some things depending on the components in it, and you should be able to study that, and that is one of the things we will do in this class, and you can see why functions are useful to know for a course like this. Okay. So, this function is called a step function in our parlance. Okay. So, we would call it a step function, and the step at 0 is equal to V. It jumps, so you can see why I call it a step function, right. There is a step at 0 and the height of the step is equal to V. Okay. So, you will learn very nice notation for functions like this. These are very important functions and they show up time and again in many of our analysis. Okay. So, we will come back and visit this function once again later on when I show you a slightly more complicated circuit and show you how to analyze that. But for now, let us keep continuing ahead and go beyond these kind of constants and simple functions and start looking at AC sources. Okay. An AC source, you might have seen AC voltage source is a little bit more interesting than a DC voltage source. The notation probably is similar to before. You might use different notation here, but this is the notation, and in fact the voltage across these the two ends of a AC voltage source is not constant over time. On the other hand, it takes a sinusoidal shape, and it is very common to write it in this fashion. Okay. So, the voltage V of t across an AC voltage source could be something like I do not know, V, let us say sine 2 pi f naught t. Okay. So, that is a lot of stuff I wrote down there. So, let us first try and think about what this function is. Okay. So, the most interesting thing I wrote here is sine, and then I guess 2 pi f naught t. You may, if you have not seen these things before, this would be very new to you. Basically, this is the sinusoidal function or the sine function, which is a trigonometric function. Okay. Okay. So, let us just quickly see definitions of the trigonometric function and how we will think of the argument of the trigonometric function, etc., etc. Okay. So, the most common definition you might have seen from your high school is if you take a right angle triangle. Okay, this is a right angle triangle, and if this angle is theta, okay, and let us say we call these things ABC. Okay, you have a right angle triangle ABC and the angle here is theta, then you might have learnt that cos theta is the adjacent side divided by the hypotenuse, and sin theta is the opposite side divided by the hypotenuse AC. Okay. You might have learnt it like this. This is your basic trigonometry, but for the purposes of this class, it helps to think of the sine and cosine in the two dimensional plane and to think of the unit circle on it. Okay. So, let us look at that. Okay. So, here is the two dimensional plane and here is the unit circle. Okay. So, I am not drawing it very perfectly, but you can imagine that this is a unit circle. Okay. Unit circle meaning that the radius of the circle is 1. Okay. And how do I think of sin theta and cosine theta? If you take any point, okay, if you take any point on the unit circle, let us say which is at an angle theta, what is cosine theta? It turns out if you drop a line like this, that point's x coordinate is exactly equal to cosine theta, and if you drop a line on the y axis, that point's y coordinate is exactly equal to sin theta. Okay. This is the same definition as what I have done here with the triangle. You can quickly see that, right. You can see that this length is 1. So, the length of the hypotenuse is 1 and this is the angle theta. So, clearly cosine theta is the adjacent side divided by the hypotenuse, which is exactly cos theta. So, this adjacent side itself is cos theta, and that is the x coordinate of this point. So, this point is actually cosine theta comma sin theta. Okay. X and y coordinate of that point are cosine theta, sin theta. Now, so this is quite important to have a good idea of what these trigonometric functions are. The unit circle is quite powerful and you can use many of these properties. For instance, quickly you see that cosine square theta plus sin square theta is going to be equal to 1, etc., etc., all those things you might be able to see here. And there is one more thing I want to point out. The angle theta is typically measured in radians. In serious mathematics courses and serious electrical engineering courses, we will always measure the angle theta in radians. Okay. So, you might if you want me to remind you of what radians are, 360 degrees equals 2 pi radians. Okay. What is 360 degrees? You start from here on the x axis, and if you go 360 degrees, you have gone one full circle around this circle, right. So, one full complete circle you have finished around this and that is 360 degrees, and that is equal to 2 pi radians. Okay. So, if you want me to show it once again, okay. So, this is the angle here is 0 radians, the angle here is pi by 2 radians, the angle here is pi radians, the angle here is 3 pi by 2 radians, and what is 2 pi radians? It is back here again. Okay. What about the angle, let us say here, if you want the angle pi by 4, that is going to be 45 degrees. Okay. Pi by 2 is 90 degrees, pi is 180 degrees. Okay. So, it is good to know these things, and 60 degrees is pi by 3 and 30 degrees is pi by 6. Okay. 120 degrees is 2 pi by 3, etc., etc. Okay. So, you should have this comfort of going between radians and degrees if you are not used to it, and start thinking in terms of radians from now on, because radians is what you really need to understand what is going on here. Okay. So, now you can quickly see that as I increase theta starting at 0, as I increase theta, cos theta starts at 1 and slowly starts decreasing. When I get to pi by 2, cos theta becomes 0. Look at what happens to sin theta. When I start at theta equal to 0, sin theta starts at 0, and then as I increase to pi by 2, sin theta becomes 1. Okay. And how does that increase happen? It happens in a nice smooth way. And then what happens beyond pi by 2? Beyond pi by 2, sin theta starts decreasing from 1 and it goes to 0 at pi. What happens to cos theta beyond pi by 2? It starts going negative, and at pi cos theta becomes minus 1. Okay. So, all these things are nice and easy to study if you remember the unit circle. And another interesting thing is, suppose you go through one full circle 2 pi and then start off again, what would happen? If you go through one full circle of 2 pi and then look at 2 pi plus theta, you come back to the same theta, right. One full circle is back to the same place, 2 pi is the same as 0. So, after 2 pi, sin theta and cos theta start repeating themselves. So, both of these functions are periodic with period theta. Okay. So, all these things are nice observations one can make. Periodic with period 2 pi, I am sorry, I said period theta, periodic with period 2 pi. Okay. So, these are nice things to know about the trigonometric functions. These are crucial functions, we will see them again and again in our class. So, let us try and plot them versus t. Okay. So, for instance, I have written here sin 2 pi f naught t. Okay. So, now this is a very standard way of writing sinusoids for AC sources. When you write it like this, t is of course the time variable that changes from minus infinity to infinity, any time is possible, negative time, positive time, t equals 0, and this f naught is called the frequency. Okay. And it has the unit of hertz or second inverse. Okay. So, typically your AC source, high voltage AC source, the power line AC source is 50 hertz, and you might have other oscillators in your circuits which oscillate at kilohertz or megahertz or even gigahertz. So, f naught is the frequency of that. So, if you want to sketch sin 2 pi f naught t versus t, let us see how it looks based on what we know about sin and cos. Okay. So, this is an important and easy plot to remember. You might know this, I am sorry for repeating that, but it is good to see it once so that we are all on the same page. Okay. So, v times sin 2 pi f naught t, and let me draw this axis here 0. So, let us try and plot v sin 2 pi f naught t versus t. Okay. So, the crucial points here are when 2 pi f naught t equals 2 pi, okay, and from there you see t is going to be equal to 1 by f naught. Okay. And the other crucial point is when 2 pi f naught t equals pi, and that is going to be 1 by 2 f naught. Okay. And then 1 by 4 f naught corresponds to 2 pi f naught t equals pi by 2, and we know from the property of the sine function, sine is going to increase to pi v and then fall down to 0 at pi, and then do the exact same thing on the other side. Okay. And this is going to be minus v, and that is how the plot for sin 2 pi f naught t versus t looks. Okay. This f naught is called the frequency, and this 1 by f naught is called the time period, fundamental period of the sinusoid. Okay. So, one interesting exercise you might want to try is you might want to plot, let us say for instance v cos 2 pi f naught t on the same diagram. If you do that, how would that work out? The red plot, it is going to start at v, it is going to be 0 down here, it is going to be minus here, and then it is going to be back up like that. Okay. So, in fact, if you know about these functions sin and cos, they are actually shifted versions of each other. You take the cosine and then shift it to the right by pi by 2 or 1 by 4 f naught, you will get the other function. Okay. So, you might know these things from your knowledge of sinusoids. Okay. So, this is the sinusoidal function, and you see it clearly shows up in a circuit. So, here is an example of a AC voltage source where the sinusoidal function shows up exactly. Okay. So, you might once again have a voltage source, an AC voltage source, okay, which is turned on, switched on at time t equal to 0. That might happen. Okay. So, maybe this is v sin 2 pi f naught t, but it is turned on only at t equal to 0. In that case, what will happen to the potential difference between these 2 points? It is going to be V of t equals 0 for t less than 0, and it is going to be equal to V sin 2 pi f naught t for t greater than or equal to 0. So, now this is a typical occurrence in many circuits that you might build. There is going to be a AC voltage source which you turn on at a particular time t equal to 0, and you want to be able to analyze it. And for things like that, you need to deal with slightly more complicated functions like this. How will this function look if you want to try and plot it? It is going to be 0 for t less than 0 like before, but then at t equal to 0, t greater than 0, it starts oscillating and you get this sign there, right, and this is going to be V, this is going to be minus V, and the x axis you can plot similar to before. So, this is how this function V of t is going to look. Now, if you have some circuitry connected to this voltage source on this side, what happens? What is going to happen? How are the voltages across the different components going to behave? Now, that is important to study, and we will do that as part of this course, and you can clearly see you need to be comfortable with functions of this sort. Okay, how do these functions behave? How do they affect circuit components? These are important questions that we need to answer. Okay. And so hopefully you see the importance of knowing about functions, knowing about trigonometric functions, and being able to plot them, being able to think of them, and that is going to be useful in a circuit.